Okay, everyone. So I'm today going to talk about how to draw Lewis structures. So I've talked about Lewis structures, what they represent, how they're, sort of what the lines and the dots and everything represent, and sort of the nature of covalent bonding. But now I'm going to talk about an actual systematic procedure for drawing these things. So we'll be able to, when you see a molecule, you'll be able to put it together and draw it without any trouble. Now, one thing I will say about this procedure, this is one of the few times that I can say you kind of don't have to think all that much. If you just do the steps in order, you will get the right answer. You will always get the right answer. Another thing to be aware of is that we're not putting them together sort of the way I showed you previously. Electrons are really fluid. So we're not going to be really worried about carbon making sure it keeps its 4 and oxygen making sure, it keeps the ones it came with. We're going to move them around a little bit more. So let's just go ahead and get started and you'll see how this all falls out. So the way you draw Lewis structures is, first, you have to determine the number and type of each atom. So I'm going to work with a pretty simple one to start with. And so we're going to start with CF4, and I'm going to keep jumping back and forth between this slide and the directions. So determine the number and type of each atom. So that's fairly simple. So it's 1 carbon and 4 fluorines. So there it is. And so now what we'll do is the next step is to use the given connecting pattern to draw an initial structure. So this can be probably the trickiest part. So most of the time, we have to figure out how the atoms are attached to one another. So most of the time, carbon's going to be in the middle. Carbon tends to make 4 bonds. Some rules that will really help you. Fluorine only ever makes 1 bond, so it's never going to be in the middle. It's always going to be on the outside. Hydrogen also only ever makes 1 bond, no exceptions. And as a rule, when you look at the periodic table, as you go from left to right and bottom to top, so the bottom left to the upper right, you have more of a chance of the ones on the left and the bottom being in the middle. And usually the element listed first, barring hydrogen, of course, is usually the one in the middle. So when in doubt, the element listed first, and you'll see why this all correlates at the end of this chapter. But this one would be in the middle. So carbon's always going to be in the middle. And usually if you see one element and then, it's like 1 of one element, 1 atom of one element, and then some number of another that isn't 1, then usually it's the second one around the first one. So, and we'll see examples. We'll do a lot of examples of this. So we're going to say that the carbon is in the middle and the fluorines are on the side. Now, it doesn't really matter how you orient this, but there's 4 fluorines all in the same direction. It doesn't really matter. Oh, and additionally, if it's any more complicated than that, I will give you the pattern. I will tell you how they're connected. That's not something I expect you to put together. You will be given that pattern to draw the structure. So now what we're going to do is we're going to take all the valence electrons that all of the atoms bring, and we're going to put them in a pot. So this is very communal, right? They don't really worry too much about possessing their own. Each element is going to get its own, or not get its own, it's going to contribute to the communal fund of valence electrons. So carbon, of course, is going to bring 4 electrons. And each fluorine is going to bring its 7 valence electrons, but that's going to be times 4. So that's, 28 plus 4 is 32 valence electrons. So we're going to have 32 valence electrons to work with. Now, as I said, we are not going to worry about making sure that the ones that fluorine brought, fluorine gets. We're going to use these very communally, it's very socialist. We're going to distribute these to make sure everyone gets what they need. So that's our goal. We're going to distribute them out so everyone gets what they need. And we have rules for how we distribute those out. Okay, So I'm going to place 2 electrons between atoms that are attached, and you can actually do this when you make the connecting pattern. But you have to realize that these are the electrons that were used. This is going to come out of our 32 for CF4, right? So I'm going to make here, 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 here. And each line represents how many electrons? 2 electrons, remember? So I've drawn 4 lines, which means we have used up 8 of the valence electrons, which means I now only have 24 left. Making sure I'm doing my math right. Yes, we only have 24 left. Then what we're going to do is we're going to use the remaining electrons to give every atom an octet. We're going to put the valence electrons on the remaining atoms in pairs. We always put them in pairs, so I'll show you how that works. Now, extra little rule. Always start with the atoms on the outside and work your way in. So atoms on the outside get first priority. Now, of course, hydrogen, which we don't have any hydrogens here, doesn't need any valence electrons to make. Hydrogen just having its bond gets its 2 electrons. But everything else needs 8 valence electrons. So I'm going to start over here. 1, 2, 4, 6. So that fluorine is now satisfied. It's got 8 valence electrons. 2, 4, 6, 8. So I've used up of our remaining 24, because we used 8 for these 4 bonds. We've got 24 left. I've used 6, 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. Okay. Now what we have to do at the end of all this is we have to check and see if everyone is happy. So there's 2 things. You can check to make sure you got the right answer. There's 2 things you're checking for. 1, do you have the right number of total valence electrons on the structure? We should have 32 total, no more, no less. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32. Okay, that's right. Now we need to check every single atom and make sure that it's got its octet or duet for hydrogen. So 2, 4, 6, 8 for that fluorine. That fluorine's happy. 2, 4, 6, 8 for that fluorine. That fluorine's happy. 2, 4, 6, 8, 2, 4, 6, 8. And now let's check carbon to make sure carbon's okay. 2, 4, 6, 8. Every atom has gained its octet. Every atom is happy. Okay, I'm going to erase this. I'm going to do another one where we'll have something. It won't work out quite so nicely. We'll have to have a couple extra rules. Okay, so now we're going to do the structure for CO2. Now remember what I said. Carbon is almost always in the middle, and the oxygens, so these oxygens will be on the outside. So I'm going to have C, and I'm going to go ahead and just draw the lines to show that they're there. Now, total number of valence electrons. Carbon is bringing 4, and each oxygen is bringing 6. So I've got 4 plus 12 is 16. I think I did all that right. Yes, we have 16 valence electrons total. We have already made 2 bonds, which uses up 4 of them. So I've got 12 valence electrons left. So now I'm going to start putting electrons down. Now remember, I said start with the outside. Oh, there's one other thing. Don't do this. Don't go 2, 4, 6. Don't jump around. Once you start on an atom, finish its octet before moving on to the next one. And start with the atoms on the outside before you move into the middle. So 2, 4, 6. That's full. 8, 10, 12. And now we'll move to carbon. I can't put any more electrons down. I can't. I've used up all of my valence electrons. Remember, I'm supposed to have 16 for the whole structure. 2, 4, 6, 8, 10, 12, 14, 16. That's all I get. Now we're going to check. So I've got the right number of electrons here. Now I'm going to check to see how each atom is doing. So oxygen, 2, 4, 6, 8. Oxygen's good. This oxygen, 2, 4, 6, 8. This oxygen's good. Carbon, 2, 4. We have a problem. We really have a problem because we can't just add more electrons. Or because we can't, I mean, carbon doesn't have enough. Now, if I just add more electrons, what's the problem there? I'm now adding extra electrons. What I'm making is I'm now making things with negative charges, right? I'm making ions now because I'm adding electrons that we don't have the protons to neutralize, right? So we only have this number of electrons to work with. So the only thing I can do is I'm going to have to make the oxygens share a little bit more. They're going to have to help. So what I'm going to do is this is where double bonds come from. So this is really critical. You do not make double bonds before this point. Double and triple bonds, you don't make them before you have all of the electrons down and written on the structure. This is critical. If you start making double bonds early, you're going to get all mixed up. So what I'm going to do is I'm going to move these two electrons to here. So I'm making oxygen share more. So you have to make sure you erase them from the atom that's sharing and then make the double bond. Otherwise, you would have oxygen would have 10 electrons, and you'd have too many. It would just be a mess. So oxygen, though it doesn't get as many to itself, right? It still has 2, 4, 6, 8. Oxygen didn't lose any electrons in this process. But carbon gained 2. Carbon has 2, 4, 6 now. Now, I can do this again. And I actually have a couple of different ways that this could happen. I'm going to show you 2 possible examples. There's 2 things I could do. I could either come over here and make this oxygen share, or I could come over here and I can make this oxygen share twice for a triple bond. Now, I want to say, both of these are perfectly acceptable Lewis structures. They are valid, legitimate Lewis structures. They are not incorrect. Neither one is incorrect. One of them is better than the other, and probably not for the reasons you think. This one up top is better. So this is a better Lewis structure. This is a better one, and not because of the symmetry. Atoms don't really care about symmetry so much, but the reason is, remember I was talking about how many bonds atoms like to make? Oxygens prefer to make 2 bonds if they can. Carbon is going to get 4 either way, but this one has both oxygens making its preferred number of bonds of 2, whereas this structure has one making 3 and one making 1. It's not as good. That said, if you put this bottom structure on a test, you would still get full credit. It is perfectly valid. Let me show you another one where you have where the asymmetry is actually necessary. Let's do CnCl. This is kind of a weird one, and I'll tell you right now, well, you might be able to guess. There's 3 atoms, one of them has to go in the middle. Remember what I said earlier? Which one should probably go in the middle? It's going to be carbon, and you're going to have a nitrogen and then a chlorine out here, so we can make our bonds. So now we got to add all these up. Right? So carbon is providing 4, nitrogen is providing 5, and chlorine is providing 7. So I've got 9, I have 16 again. We're going to get basically the same thing, right? 2, 4, 6, 8, 10, 12, 14, 16. So this time I didn't subtract off of here. I just used these when I was counting. Same basic idea. And again, I have carbon that doesn't have enough. Now, I'm in the same situation where I could make either, I'm going to draw it again down here. I could make either 2 double bonds or a triple and a single. Which do you think is probably the better Lewis structure? They're both valid. They're both totally okay because they have 2, 4, 6, 8, 10, 12, 14, 16, and nitrogen has 2, 4, 6, 8, carbon has 2, 4, 6, 8, chlorine has 8. They both satisfy all the rules for being acceptable, but the better one is actually this one down here. The reason it's better is because nitrogen being in group 5A, prefers to make 3 bonds if it can, and chlorine prefers to make 1 if it can. This is not wrong, though, but this is a better one. That's all. Let's see if there's any other good. Well, I'm going to jump right to practice. So, practice drawing these. One thing I will say, whenever you see these acids, see these here, let me show you how some of these are attached before. So this is a carbon, carbon, and then, so this is carbon, carbon, and then each carbon has 2 hydrogens. Whenever you'll see this pattern a lot. You'll see what is effectively a polyatomic ion with H's put in front. The H's are always attached to the oxygens, not the nitrogen, and only 1 on each. So when you see this, this is this. And I think everything else is pretty self-explanatory. So given this, go ahead and try drawing the Lewis structures, putting the electrons on, and then I'll come back and do these. Okay, so pause it. Okay, hopefully you're done now. So let's start with the first one, O2. We've got 2 oxygens. Each oxygen is providing 6 valence electrons, right? So I have a total of 12 valence electrons to work with. Minus the 2 from the bond that I've made, I've got 10. So I'm just going to pick one of, there's no central atom, I'm just going to pick one and go with it. 2, 4, 6, 8, 10, oh crap, I'm out. I can't add anymore. So I have to make a double bond. Right? And now we have 2, 4, 6, 8, 10, 12 total valence electrons, which is what we're supposed to have. This oxygen is happy with 2, 4, 6, 8. This oxygen is happy with 2, 4, 6, 8. Excellent. Next one. Oh man, I totally gave you the wrong structure. I'm sorry. Hopefully you noticed that. I gave you C2H4. I'll do that structure actually. So the one I actually drew is different from the one we'll do. We'll do both. So the one I actually drew looks like this. And so the one I drew would have 4 electrons from carbon, 4 electrons from carbon, so that's 8. 1 from each hydrogen, so 9, 10, 11, 12, so we'd have a total of 12. Hydrogen has all it can stand. We've used up 2, 4, 6, 8, 10. I only have 2 more electrons. I'll put them on one of the carbons, but now this carbon doesn't have enough, so I have to make a double bond. And I also have to draw in the rest of the carbon. So there it is. Now the one I actually meant was this one. And this is going to have a slightly different number of valence electrons. You have 4 from each carbon, so 8. And then hydrogen, hydrogen gives me a 10 total. 2, 4, 6 are already used up. We have 4 left. I'm going to put 2, 4 there. This carbon only has, so this carbon's totally happy. 2, 4, 6, 8, it's fine. This carbon only has 4 valence electrons. I need to share, right? Oops. I need to share, right? So now this carbon still only has 6, 2, 4, 6, 8. This carbon's still happy. It needs to share again. 2, 4, 6, 8, 10 total electrons, and each carbon has 8. Okay, coming down here. HNO3, let's figure out our total. I'm going to kind of clean up the page a little bit. Let's figure out our total number of valence electrons. The nitrogen has 5, which I'll write down momentarily. Nitrogen has 5. Each oxygen has 6 for a total of 18, plus 1 from the hydrogen is, let's see, is that 24? I think it's 24. We've used up 2, 4, 6, 8 of the valence electrons so far, which leaves us with, what is that, 16? Okay, I think, hopefully I do. I'll find out soon enough if I didn't do my math right. 2, 4, 6, 8, 10, 12, 14, 16. Okay, so let's double check. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. 24 total electrons, that's good. Now if we look, this oxygen, happy, 8. This oxygen, happy with 8. This oxygen, happy with 8. Hydrogen only needs the 2. And nitrogen has 2, 4, 6. Okay, well, this is a problem. Well, all we have to do is make a double bond. Now, we could do that from any one of these oxygens. Now, thinking about what I told you earlier, which one would be the right one to use? A lot of people say it's this one, and they do it, again, because the human brain loves symmetry. They don't want to break the symmetry of these two oxygens being the same. But if you look at it, now we have one oxygen making one bond, one making one bond, so two making one bond each, and this one making three. None of the oxygens are especially happy with this arrangement. But if I take this one or the other, it actually doesn't matter which of the other two I use. Let me try to clean this up a bit. Right? Now this oxygen is making one, so it's unhappy, but this one's making two, this one's making two bonds. So the most number of oxygens are happy as can be. That said, the other structure is not wrong. You would not lose credit for writing it. Oxygen 2, 4, 6, 8, 2, 4, 6, 8, 2, 4, 6, 8. Nitrogen's now happy with 2, 4, 6, 8. Total, 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. Right? Okay, CH4. How many valence electrons should we have total? We have 4 from the carbon, 4 from the hydrogen, so that's 8 total. Carbon, 4 hydrogens around it. How many electrons have we used up making the bonds? That's right, we've used up all 8 of them already. We have none left. But that's really not a problem because carbon has 2, 4, 6, 8, and it's fine. And each hydrogen has its 2, and it's fine. Okay, SO3. Let's take a look at SO3. Now, this is to make sure you understand, this is not sulfate. This is sulfur trioxide. This is a different structure. It doesn't have the charge. The charge would be written. So sulfur has 6 valence electrons. Each oxygen has 6 for 18 plus, so that's 24. So I've used up 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. Only sulfur isn't happy, and since all 3 of these oxygens are exactly the same, it really doesn't matter which one I make the double bond from. So there you go. That's probably gone on a little long, but there you go. Hopefully that helps. So if you follow these rules, put the atoms in the structure, find out how many valence electrons you have, add them starting from the outside going in, and then make double bonds at the end, double and triple bonds at the end if you need to. That's how you do it. And you can always check how many valence electrons you have at the end, whether it matches how many you should have, and make sure each atom has its octet. So there you go.